Okay, welcome back. This is Mr. Hassan's Maths channel. This is question number 7, which is the final question on this October-November 2023 mechanics paper, which is paper 4, variant 3 from the Cambridge 9709 syllabus. And this question here is about connected particles and inclined planes. It says particles A and B of masses 2.4 and 3.3 kilograms respectively are connected by a light an extensible string that passes over a smooth pulley which is fixed to the top of a rough plane. The plane makes an angle of theta degrees with the horizontal ground. Particle A is on the plane and the section of the string between A and the pulley is parallel to the line of greatest slope of the plane. Particle B hangs vertically below the pulley and is 1 meter above the ground as shown in the diagram. The coefficient of friction between the plane and the A is mu, between the plane and A is mu. It is given that theta is 30 degrees and the system is in equilibrium with A on the point of moving directly up the plane. So there's a few things that we need to understand, which will be better for us to understand. Okay, so first of all, you have these particles, which means the weight acts through a single point. Okay, that's one thing. So the weight on these particles acting through a single point. They're connected by a light inextensible string. Light means that the string, we ignore its weight, which would mean that the tension all the way through the string, all right, from on each end is going to be the same. The tension at this section to that section will be the same. Okay, the tension in that section will be the same. It's inextensible, meaning that there is it doesn't stretch. All right, it's not elastic, doesn't stretch. So therefore, all particles attached to the string will be traveling with the same magnitudes of velocities and accelerations. It passes over a smooth pulley, means the tension on either side of the pulley will be the same. There's no friction in the pulley. That means the tension on either side of the pulley will be the same on that string. Particle A is on the plane, and which is fixed to the top of a rough plane. The rough plane meaning there's going to be friction between A and particle A is on the plane, and the section of the string between A and the pulley is parallel to the line of greatest slope. Now, some people don't understand what that means and they get confused by it. You don't really need to know what it means, but just imagine we have our ramp slope that we're looking at from an angle. So this is like the particle. So the string is basically not at an angle. It's basically straight up, okay, parallel to the line of greatest slope of the plane. So it's not diagonally going across. It's going straight up, parallel, you say, to the sides. The shortest distance between the particle on the top of the plane, not at an angle. That's what it means, something like that. Okay, so that's what that means here when it says parallel to the line of greatest slope of the plane. Particle B hangs vertically below the pulley and is 1 meter above the ground as shown in the diagram. The coefficient of friction between the plane and A is mu. So we got all of this information and these modeling assumptions that we should know. So what I'm going to do now, I'm going to got the diagram over here so I can draw the forces on and see my working easier. So first I'm going to draw the main forces that are acting on the particle. And those main forces are basically the weight of the two particles. So you've got the weight of B and the weight of A. Okay, so the weight of B is 3.3 G, which is going to be 33 newtons. I'll just keep it as 3.3 newtons. And the weight of A is going to be 2.4 G newtons. Those are the weights. You also have the tension in the string. So the tension pulling up on the particle B would be acting this direction. Okay, so that's the tension in the string there. And this tension will be the same because we have a light string and we have a smooth pulley. So that tension here will be the same in both cases. Okay, we also have the reaction force between the particle A and the plane, which always acts perpendicular to the surface. So that's the normal reaction force. And we have also another force, friction, because it's a rough plane and it's on the point of moving up. If it's on the point of moving up the plane, then that means friction is opposing that motion that's about to take place, so it's going to act down the plane. So if it says on the point of moving up, then we have friction acting down, and also what we know about that frictional force, it is its maximum value because it's on the point of moving. It's just about to move. So if something's moving on a rough plane or is just about to move on the rough plane, then we say that F max has been achieved. The maximum value of friction in that situation has been achieved. And we know that F max is equal to mu times R. All right. And we have to find mu here. So that means we need to find what R is, and we need to find what F max is, and then we can find what the friction, we can find what mu is. Okay, so now let's take some of these forces here and resolve them parallel and perpendicular to the plane so that we can start answering the question. So now I'm going to make a little line here. All right, just to resolve the forces. I know that this angle here, it says it's 30. So this is going to be 30 degrees. So this here is going to be 30. Now, if I resolve this force, this weight, and I resolve it in a direction which is perpendicular to the plane, which is going to be in this direction here. Let me change it to a dotted line, okay. And I also resolve this same force, but I resolve it parallel to the plane. Again, let me change it to dotted. Okay, so those are not new forces, but those are that's the force of the weight which is resolved parallel and perpendicular to the plane. When you're resolving perpendicular to the plane here, because I'm given the angle 30 degrees and I have to go into the angle, I'll use cosine. So 2.4 G, okay, which is 2.4 G times cosine of 30 degrees. And if I resolve parallel to the plane, I'm going to use sine. So 2.4 G times sine of 30 degrees. Okay. And we know that this whole thing is in equilibrium, but on the point of moving. That's why we know that F max has been achieved. So if we know that it's in equilibrium, there's no acceleration taking place. So if I consider B, for example, and I resolve the forces vertically, I can say T is equal to 3.3 G newtons, which means T is equal to 33 newtons. So I know that's what the tension is. All right. Now, how is that going to help us? Well, it's going to help us if we look at the second equation or the second object A. Now, if I resolve these forces perpendicular to the plane, then I know that R is equal to, and you're going to have 2.4 G times cosine of 30. Okay, so we can find what R is exactly from this. We have 2.4 times, or that's going to be 24 because it's multiplied by 10. So we use 24 times cosine of 30, which gives us 12 root 3. I'll leave it in this exact form, 12 root 3. Okay, now if I resolve the forces on A, it's on the point of slipping up, so I'm going to resolve the forces parallel to the plane upwards. Then the forces acting upwards are the tension, and that's equal to the forces acting downwards, which is F max, which we have to find for us to be able to answer the question. Plus, the other one acting down is 2.4 G times sine of 30. Okay, so now I know the tension is 33. So I can say F max is equal to 33 minus this, which is 24 times a half. So 33 minus 12 is 21 newtons. Okay, so I know F max is 21 newtons. So therefore, I know as F max is equal to mu R, therefore mu is equal to F max over R, which is equal to 21 over 12 times root 3. And that will give us our value of mu. And hopefully it will be what we had to show, which is 1.01, corrected 3 significant figures. So let's see what happens. We have 21 over 21 root 3, over 12 root 3, sorry. Now what does that give us? It gives us 7 root 3 over 12. 7 root 3 over 12 as a decimal. That gives us 1.01036. 1.01036. As we can see, to 3SF, that gives us mu equals 1.01, which is exactly what we had to show from the beginning of the question. And so that's part A completed of this question. And now we're going to move on to part B. Now, part B of this question here, it's told us that the angle here now is 20 degrees and mu is 1.01. The system is released from rest now with the string taut, and we got to find the total distance traveled by A before coming to instantaneous rest. Now, so what's going to happen here is this is going to be released and it's going to move. Okay, so now what's going to happen is there's going to be an acceleration which is going to act downwards for B and up the plane for A. Okay, but what's going to happen is B is going to hit the ground. Now, when B hits the ground, we'll have a new situation. So first, this is going to travel 1 meter up. It's going to travel 1 meter up, but then we'll have a new situation where the tension in the string will be gone, because when this hits the ground, the string won't have any more tension in it. So this particle after 1 meter is going to just travel up the plane, and it's going to decelerate because only forces acting on it would be the friction and the component of its weight down the plane. So we got to basically try to find out, well, we know it travels 1 meter in the first part of the journey. So we're going to, let's call this point P and then Q and then R. So from P to Q, I know the distance is 1 meter, right? I know that that's how much it's moved. Okay. Now, so that's what we know about P to Q. Now, for Q to R, all right. So P to Q, there's one situation happening, which is going to be according to the acceleration when, before B hits the ground. But then from Q to R, what's going to happen is we know that it's going to reach 0 meters per second by the time it comes to instantaneous rest. So what we need to find is the speed of the particle A when it reaches Q. That will be the initial speed of the particle A once it goes past Q, when the string becomes loose, and once B has hit the ground. And then the final velocity will be 0. So we need to find, we know that the distance travels 1 meter, but we need to find what velocity it's traveling at the point when B hits the ground. Okay, so how could we do this? Well, we need to work out the acceleration of the system. Okay, so we could work out the velocity of B as it hits the ground. It will be the same as the velocity as A as it reaches that point. We could do that, and that's fine. Okay, that might be a bit easier for us, but in any case, we need to do some resolving of forces, because we have to find the acceleration of the system for us to be able to find the speed that it reaches by this point. Okay, because if we're going to use SUVAT for this, we know this is 1 meter, we know this is 0 because it's released from rest, as it says here. If we know the acceleration, we can find what the speed is at this point, which will be the initial speed of Q of the particle as it carries on from Q towards R. Okay, so that's what we need to do now. We need to find the acceleration of this system. So what I'm going to do is just get rid of some of these things here. So it's just for illustration purposes there. So this is the acceleration we're trying to find. This is 20 degrees this time. And let's draw the forces in now. So you got the weight of A and the weight of B. Okay, those two forces there, which are 2.4 G and 3.3 G newtons. Okay, now you have also the same, you have the tension in the string. You have the tension in the string pulling up this way here. these will have changed their value now because of the difference in the situation now, because the angle is different. That's going to be now your F max. Now F max will have been achieved. You're going to have your reaction force acting upwards. And you're also going to have the component of these forces acting perpendicular to the plane and parallel to the plane. So you're going to have this. Let me just make that better. You're going to have this. You're going to have the weight. So you're going to have, now this angle is now 20 degrees. So now this becomes 2.4 G times cosine of 20. Why? We're going into the angle, and here we're going away from the angle. So 2.4 G times the sine of 20. Okay, so now we have all the forces acting on the particles, and we know it's accelerating. So we need to find the value of that acceleration first. Now, to find the value of that acceleration, what we can do here is we can resolve the forces again. And this time for B, there's a difference. T is not equal to 3.3 because now it's accelerating. So if we resolve the forces in the direction that it's moving, which is downwards, which we should always try and do, we have the downward force, which is 3.3 G, minus the tension, equals the mass of the particle, which is 3.3 times the acceleration. So that's one equation now, which we can't find T with straight away because we have an A in there now. It's not the same as the last situation where it was in equilibrium. So T is equal to 3.3 G. Now that's a mistake that many students made when answering the question. They assume the tensions would be the same as in the first situation, but the situation has changed now. There's different angle acting. Therefore, that changes the whole situation about the forces in the diagram. So don't make that mistake. That's a big mistake that many students made. Now I'm going to consider A, and I'm going to consider perpendicular to the plane, in which case we have R equals, and this is 2.4 G times cosine 20 this time. Okay, that's what R is going to be. I'll leave it like that for now, and we'll round it when we need to. And now we're going to look at A, and now we're going to resolve parallel to the plane upwards as it's moving upwards. So we have T, we have minus F max, we have minus 2.4 G sine 20, and that's equal to the mass times acceleration. So 2.4 times A. So remember, we don't say the upward forces equal to the downward forces this time, because now it's not in equilibrium, it's moving. So we're using F equals ma. F equals the mass, the resultant force equals the mass times acceleration. So this is the resultant force equals the mass times acceleration. So now we have, let's put in what F max is. Now we know that F max is equal to mu r. So F max is equal to mu r. So I can say F max is equal to mu r, which is going to be 1.01 times 2.4 G cosine 20. Okay. So I'll leave it like that for now again, as I said, because I don't want to round anything. So I've got here T minus 1.01 times 2.4 G cosine 20 minus 2.4 G sine 20 equals 2.4A. Now with this, we can find the acceleration because we have two equations. So what I can do is I can use substitution if I want. I can say this means that T is equal to 3.3 G minus 3.3A. So I can replace the T with that, or I can add the two equations together. I think it's easy to think about it this way. So I'm going to replace this instead of the T over here. So I have 3.3 G minus 3.3A minus 1.01 times 2.4 G cosine 20 minus 2.4 G sine 20 is equal to 2.4A. So now I can bring the A's together. So I have 3.3 G minus 1.01 times 2.4 G cosine 20 minus 2.4 G sine 20 is equal to 2.4 plus 3.3. That's going to be 5.7. 5.7a. I've added this to both sides. Now I can just find out what this is. and just divide by 5.7. All of these I know the values of, so hopefully that will give us our correct answer. So A is going to be equal to, let's see what we get. We're going to have let's say 33 minus 1.01 times 24 cosine 20, because G is 10, remember. Okay, minus 2.4, or we can say 24 better, 24 times sine of 20. Okay, and then we can divide that by 5.7. And that gives us the acceleration, which is 0.35322. So 0.35322. So we say the acceleration, we don't need to round it because we're going to use this value to find now the speed of A as it gets to the point where it's moved 1 meters. Okay, so we know that if we use Suvat, now, I'm gonna call this point, P and Q. So I'll call it between P and Q. This is between P and Q. So S is 1 meter, U is 0, is relief from less, V is what we have to find, and A is 0.35322. So we don't need to know what T is. Here we can say that V squared equals U squared plus 2AS. So V squared equals 0 plus 2 times 0.35322 times 1. So we can work out what V is, the square root of that. So let's take this value, multiply it by 2. Okay, and then take the square root of that. So the square root of our answer is going to be 0.8405 meters per second. So now we can consider between Q and R. Okay, now between Q and R, there's a new situation. Okay, the string has broken. So now we've got the situation where you've got your plane. Shall I draw it by hand now? You got your plane. Now the tension is gone. The tension is no more. You have the friction, you have the weight, you have the reaction force, you have the component of the weight down the plane. You have this. We know this angle is 20 degrees. We know the tension now is gone. Okay, so we only have the forces of the weight down the plane, which was, remember, 2.4 G. So this is 2.4 G times the sine of 20. And we also have, that was the reaction, that was the weight down the plane. And then we have the frictional force, which is F max, which is going to remain as it's moving. It's going to be F max. Okay, as it's moving up, it's going to be acting downwards, and F max is going to be this value here, which is 1.01. Okay, I'll just call it F max for now, and we know that F max. Okay, we'll write that down in a minute. So those are now the only forces acting on this, apart from the reaction force. So if we consider the forces acting up the plane, okay, then these two forces acting down, so the negative. So negative F max, negative 2.4 G times sine of 20 is equal to the mass, which is 2.4, times this new acceleration. Okay, times this new acceleration. So now we have minus, so F max is basically going to be this value here, which is 1.01 times 2.4 G cosine 20. So 1.01 times 2.4 G cosine 20 minus 2.4 G sine 20. If we divide that by 2.4, that will tell us the new acceleration, which is going to be, of course, a deceleration. It's going to be negative. So the acceleration is going to be, if we add these together, we have I'm going to store this in case I need it. Okay, we're going to have 1.01. Let me just put this in the one fraction. 1.01 times 24 cosine 20 minus 24 sine 20, and divide all of that by 2.4. By 2.4. And that gives us sorry. That's supposed to be a minus here. What have I done? That's supposed to be minus, negative. See, I put the calculator in the way. Let me just do that again. Okay, that's supposed to be negative. Okay, be careful about that. So actually it gives us negative 12.911. That looks better. Negative 12.911. That's acceleration. So what I'll do is I'll store that as B. Okay, so I've got the acceleration as B. This is B in my calculator, and this is A in my calculator now in my memory. So now I have my new acceleration in my new situation between Q and R, which that's when the string has become taut, and now it's just moving without the tension up the plane. So we have S, which we have to find, U, which is equal to this, because that's how fast it was moving at the point when B hit the ground, and V, which is going to be the final velocity, which is 0, and A, which we found as minus 12.911, and T we don't need to know. So again, we want to find what S is. So here we can use again V squared equals U squared plus 2AS. So we have here 0 equals 0.8405 squared plus 2 times minus 12.911 times S. So S is going to be equal to, when we divide them, this will become positive. Negative divided by negative will be positive. So you have 0.8405 squared over 2 times minus 12.911, and that's going to give me the amount it moved up the plane after that 1 meters. Okay, so we're going to take this. All right, we're going to have the answer for A. So I'll put, that's going to be, let me just, by fraction, the answer for A squared over, and you're going to have 2 times the answer for B, and that will give us our value. Hold on. Sorry, this is plus. What am I doing? That's positive. So that should be actually, I'll put a minus in front of that. So that gives us 0.0273. So S is 0.0273 meters. So therefore, the distance traveled is 1 meter plus 0.0273 meters, which is 1.027, which is 3SF would be 1.03 meters. So there we have the total distance traveled by this object from the time that it was released until the time it came to instantaneous rest. Now, many people made messes of this question because they didn't consider the fact that acceleration in this first section and in the second section is going to be exactly the same. Okay, so once it reaches Q, all right, the tension in the string becomes 0. Why? Because B has hit the ground. So there's no more tension in the string. Right, so once B has hit the ground, it's now going up, and the only forces acting on it now are the frictional force acting down the plane and the component of the weight down the plane. Some people took the component, just took it as acting under G after the tension went on the string. No, it's not acting only under G, because it's not vertically under gravity. You've got this plane, it's going at an angle. So you have friction as well. So it's going upwards, friction is acting downwards, and also the weight, or the component of the weight down the plane, is acting on it. So those are what causes this deceleration of negative 12 that we found here. And then we can now use that acceleration in our SUVAT with the velocity at which it was moving at the point which B hit the ground. So this is quite a lengthy question. That's why it's worth 8 marks. A lot of points here that are important for us to understand. And anyway, that's the answer to the question, and that completes the whole of this paper. Other questions from this particular paper can be found in the playlist that will be appearing in this area over here. Other questions from the topic of connected particles, dynamics, okay, friction. I'll put a few different playlists up here that will help you. I'll also put a playlist here for the edXL material I have on the same topic so that you can watch some of those questions. The only difference is G will be 9.8 in those questions, so have to just watch out for that, but the principle is the same basically. So there we have it. Thank you for watching. See you soon.